I am going to explain Gaussian mixture models. Think of it like this: you have a bunch of data points, and you suspect they come from several different groups, each following a bell curve, a Gaussian distribution. A GMM helps you identify those groups and the characteristics of each bell curve. It's a powerful tool for clustering data. We're using scikit-learn's say is interpret as characters. Gaussian mixture say is to analyze data. We've assumed the data is from 3 different Gaussian distributions, and we're looking at the means of those distributions. Okay, let's break down this problem. We have a model. Say is interpret as characters. Gaussian mixture say as. That's identified 3 potential underlying groups within the data. The output means gives us information about the centers of those groups. Are 3 by 2 array. That's what we need to interpret. This statement means each row in the array represents the average of data points belonging to one of the groups. Because it's a 2D array, each mean will have 2 numbers, like a coordinate. This is false. The say is interpret as characters. Gaussian mixture say is model stores covariance matrices in a different attribute. I believe its covariance is break time 200 milliseconds. This isn't what means contains. Precisely. The 2 columns of the array means each point in the data has 2 features. For instance, it could be height and weight. Incorrect. Another attribute, likely weights, would give the relative size of each of the 3 groups. This section will help you grasp the overall idea. We're focusing on interpreting the output of the say is interpret as characters. Gaussian mixture say as model in scikit-learn. Well, need to know about the say is interpret as characters. Gaussian mixture say is class in scikit-learn. No complex math is needed. It's about understanding the meaning of the output. I see 3 rows in the array, and each row represents the average values mean vector for one of the 3 groups of data points that Gaussian mixture model GMM identified. Think of it like finding the center of 3 different overlapping clouds of data. Break time 300 milliseconds. The 2 columns in each row tell us that each data point has 2 characteristics, 2 features. It's like each data point is described by 2 numbers. For example, if we were analyzing customer data, those 2 numbers could be age and income. Break time 300 milliseconds. The shape 3:2 is a simple way to express the overall organization of the array. It means that I have a 3 by 2 matrix of data, 3 rows and 2 columns. This directly reflects what I previously mentioned, that there are 3 groups Gaussian components, and each data point is characterized by 2 features. Break time 300 milliseconds. I see a 3:2 shape for the means attribute. This tells me that we're dealing with 3 Gaussian components speak because of the 3 rows speak. And each data point has 2 features or dimensions speak because of the 2 columns speak. Imagine 3 separate blobs of data points, each following a different Gaussian distribution. Each row represents the average location, the mean vector of each of those 3 blobs in 2-dimensional space. This statement is Google style name emphasis absolutely correct Google style. Each row in the 3:2 array holds the mean values for the 2 dimensions of one of the 3 Gaussian components. Think of it as the average coordinates of each of the data blobs I just described. This is Google style name assertive, also true Google style. Each data point is characterized by 2 values like x and y coordinates. The 2 columns in the means array represent those 2 dimensions for each of the 3 components. This is Google style name SAD incorrect Google style. The covariance matrices, which describe the spread or dispersion of each component, are held in the covariances attribute of the Gaussian mixture model. Speak not in means. Speak. No. That's Google style namesad, not right Google style either. The weights telling you the relative proportions of each component are kept separately in a weights attribute. The data points themselves are described by two values 2D, which can be visualized as positions on a 2D plane. Each Gaussian component is a distribution of data points on that same 2D plane. One of the three Gaussian distributions that makes up the mixture model. It's described by its own mean from the means array, covariance from the covariances attribute, and weight from the weights attribute. Another one of the three Gaussian distributions. Similar to component 1, this has its own mean, covariance, and weight. The last of the three Gaussian distributions. This too has its mean, covariance, and weight that characterize this distribution. I am going to explain how to interpret the means attribute from scikit-learn's Gaussian mixture model. This attribute is really important because it gives you the average values of your data, broken down into different groups or components. It's like finding the center of each cluster in your data. Let's talk about this shape. 3. 2 means that we have Google style name emphasis 3 Google style components in our Gaussian mixture model, and each data point has Google style name emphasis 2 Google style features or dimensions. I can imagine this as 3 different groups of data points that each have an x and a y coordinate. That statement is incorrect. The means attribute only gives us the average values mean vectors of each component. To get information about the weights, how much each component contributes to the overall mixture, you need to look at the weights attribute. This is like saying that means tells you where the centers of your clusters are, while weights tells you how many data points are in each cluster. I see that our Gaussian mixture model is using 3 Gaussian distributions to model the data. We call these distributions components. I can think of these like 3 different bell curves that are mixed together to fit our dataset. Each component represents a group in our data. Each data point has 2 features or dimensions. We can picture this like plotting our data points on a 2D graph with an x-axis and a y-axis. Each data point is located by its coordinates on this graph. This is true. Each row in the means array gives us the average values for one of the 3 components. Each component's mean will be a 2-dimensional vector, which is like saying the average x and average y coordinate for the data points in that group. Google style name excited, great job. Google style. That's correct. The 2 columns represent the 2 dimensions of the data. So, we're dealing with 2 features in our data. Google style name excited, superb. Google style. This is false. The means attribute does not contain the covariance matrices. The covariance matrices which show the spread and correlations within each component are stored in the covariances attribute instead. That is like saying means gives you the center of each group and covariances gives you the amount of spread of each group. I am looking at how we interpret the output from a Gaussian mixture model. A GMM assumes your data comes from several different bell curves, Gaussian distributions mixed together. We're interested in understanding what the model tells us about those individual curves. Break time 200 milliseconds. This tells us something important. Break time 200 ms. The 2 means there are 3 separate Gaussian distributions, and each data point has 2 features. Think of it like this: break time 200 milliseconds. Imagine you are measuring height and weight of people. Each person would be a 2-dimensional point: height, weight. The GMM is finding 3 distinct groups of people based on those 2 measurements. Break time 200 milliseconds. The means attribute in scikit-learn's Gaussian mixture is giving us the average values for each of the identified groups. So, This question is about how to read and interpret this output. Break time 200 ms. Remember that scikit-learn is a popular Python library for machine learning. Speak this line explains the meaning of the array shape 3. 2 which I see in the scikit-learn Gaussian mixture model output. The 3 tells me there are 3 Gaussian distributions that make up the model. And the 2 indicates each data point has 2 features or dimensions. Google style name excited. Think of it like this: you are trying to group points on a flat surface 2D into 3 different clusters. Google style speak. Speak this sets the stage. I am working with a Gaussian mixture model GMM from the scikit-learn library in Python. A GMM assumes your data comes from a mixture of several Gaussian distributions. Think bell curves. Google style name conversational. We're trying to figure out which statements are true about a model's output. Google style speak. Speak this statement is incorrect. I know the means attribute only gives me the means average values of each Gaussian distribution. The covariance matrices, which show how spread out each distribution is, are stored separately in the covariances attribute. Google style name empathetic. It's an easy mistake to make if you are not completely familiar with the scikit-learn library. Google style speak. Speak this simply labels which answers are correct to the multiple choice question. You'll need to understand the problem more thoroughly to determine which answers are correct. Speak. Speak this labels the answers that are incorrect. Speak. Speak this is correct. Each row in the means array represents the average values for a single Gaussian component. If the data is two-dimensional, each row will have 2 numbers, the average x value and the average y value for that cluster. Speak. Speak absolutely true. The number of columns in the means array shows how many dimensions my data has. Since it's 2, it means each data point can be plotted on a regular 2D graph like an XY plot. Speak. Speak nope. The weights are not stored in means. The weights, showing the relative importance of each Gaussian component in the mixture, are stored in a separate attribute. Weights. It's important to know where to find each piece of information. Speak. I see. You are working with Gaussian mixture models GMMs. A GMM assumes your data comes from a mixture of different Gaussian distributions. Think of it like this: you have several overlapping bell curves, and your data points are scattered across them. The goal is to figure out the characteristics of each of these individual bell curves, their centers, means, their spread covariances, and how much data belongs to each weights. The question focuses on understanding the means attribute, a key part of the GMM output. This attribute gives us the center or average for each of the Gaussian distributions we found. We'll see that the shape of the array itself gives us important clues. Okay, so the means attribute is represented as a NumPy array. The number of columns tells us the dimensionality of each data point. If it's 2, it means each data point has 2 features or variables. For example, it could be height and weight, or temperature and pressure. Google style name excited. Each row gives the average of the 2 features for each component. Google style break time 300 milliseconds. That's what makes this so insightful. Let's break down this statement. Each row in the means array represents the average values for a single Gaussian distribution. Remember, a Gaussian is described by its mean average. If you have multiple Gaussians, you'll have a mean for each one, displayed as a separate row. Google style name conversational. It's like finding the center of each individual bell curve. Google style. This is false. The weights, representing how much each Gaussian contributes to the overall data, are not held by the means attribute. Instead, the weights are given by another attribute. In other words, The means attribute only tells you the average location, not the relative importance of each component. This one is incorrect too. The covariance matrices, which tell you how spread out the data is for each component, are stored in a different attribute, namely covariances. The means attribute only provides the location, not the spread of each Gaussian component. Break time 200 milliseconds. Google style NAMI emphatic. Think of it like this: means are the centers. Covariances describe the sizes of each bell curve. Google style break time 300 milliseconds. This line summarizes that we have a model with 3 Gaussian components, 3 bell curves, and each data point has 2 features. It's in 2-dimensional space. This information is essential for interpreting the shape of the means array.